Welcome to another episode of Earth is Our Home with Dr. Thomas Blaine. Today we're going to be continuing our discussion of global warming, so stay tuned. Welcome to another episode of Earth is Our Home with Dr. Thomas Blaine. Dr. Thomas Blaine is an associate professor with The Ohio State University, in which he's very active in helping us to understand global warming and the benefits and consequences. Tom, it is always a pleasure talking with you.
It's great to be here, Patrick. I appreciate being able to come on and do a series on global warming, or climate change, as it's also known. It's something that I really enjoy discussing and teaching the public about.
Our last episode, in which you helped us to introduce the different changes over millennium, and now you want to sort of focus our discussion on what has been happening since the last ice age. Is that correct?
That's correct. Yes, actually, that's exactly right. I like to go from the beginning of the Phanerozoic eon, which was about 550 million years ago. Talk about all those temperature changes that have occurred, wild fluctuations, why they occurred, and then come up through the ice ages. Why did those occur? And I think it's very important to do that for a couple of reasons. One is because people here, hasn't Earth's temperature always changed? And the answer is yes, it has. But I want them to understand why it's always changed. Then also it gives a context for what do we mean by a 5-degree Fahrenheit change, or 10 or 15? What kind of transformation of the climate does each one of those produce? You know, we hear the term global warming and then we hear climate change, and they are related. If we have major changes in Earth's temperature, we get changes not only in that, but climate changes follow. And I want to explain that to people so that they have a better understanding of what people are talking about when they discuss this issue. Patrick, we had talked about these questions. And again, this is why I wanted to address these. Isn't it true that Earth's been warmer in the past? Why are a few degrees now such a big deal? These changes occurred before. Aren't the warming and cooling cycles natural? What reason is there to believe that warming is man-made, the current warming? And where did the idea of this first come from? This is what we're answering in the entire series. And, I began on 1, 2, and 3 last time, and we came up through the last ice ages, and we're getting ready to go into a little bit more recently. In the meantime, go ahead and Google my fact sheet. Everybody that's watching, there's the address. But if you want to, it's easy to find. You can just Google, go to a search engine, Thomas Blaine, Global Climate Change, Ohio State fact sheet. The last update was 2020, so it's pretty current. I urge you to read that. We talked about last time how the temperatures have fluctuated over the past nearly 600 million years, from an average of about 12 degrees Celsius to 22. That's 10 degrees Celsius change. That's a 10 degrees Celsius change, which is 18 degrees Fahrenheit. That's 18 degrees. So think of the overall change as 18 degrees. And we're talking about right now, Earth is in a cold spot. If you look down to the right, 0 years ago, those are years ago down at the bottom right, and you can see we're cold. And we went over last time. I encourage you to watch episode 1. Inside that million, or that last few million years, specifically 800,000 years ago, when you magnify each portion of the graph, you see that there are variations. So now, in the past 800,000 years, we have an ice core from the Vostok ice station in Antarctica by the Russians and it shows the changes in the ice ages. If you look way out to the right, you'll see we're very warm. We are very warm right now. We're in an interglacial. 20-some thousand years ago, most of North America was covered by an ice sheet. So yes, these all changes, as we pointed out, are natural. We live in an unusual age and an unusual era. Overall, on the big scale of things, it's cold, but within the period of the last million years, it's very warm. We are in an interglacial. And so it's an unusual time. And when you think about it, it basically means we're kind of poised on a knife's edge. You know, if we went over into a hothouse Earth, it would be devastating. Imagine, tropical type climate in Minnesota, Northern Ohio, Montana. That's what it was 60-some million years ago when Tyrannosaurus Rex ruled the Earth. But with an Earth that warm, virtually everything we have on the planet would go extinct, because all the plants and animals we have on the planet have evolved in the current climate that we have. They can adapt over thousands of years, tens of thousands of years, but they can't adapt quickly. They can't adapt overnight. And so that's why, it's one of the very main reasons why 99.99% of all species that have ever existed are now extinct. If we fell over the other way and cooled to the point where we were 25,000 years ago, it means that ice would come down all the way across North America. We would have no agriculture. And again, you would see extinction. So,
Tom, it seems that the Earth rotates around the sun. It seems that for the last hundreds of millions of years, we have had a similar trajectory where the Earth is the same. Why does it happen that we have at periods of time ice ages and then warm ages? Is it because of the atmosphere? Is it because of what is the reason for that?
No, but that's a great question. But the answer is no. The Earth's orbit around the sun is not constant. The fluctuations here are caused by what a Serbian astronomer figured out. His name was Milankovitch. He figured out that Earth's orbit goes through cycles. So, Patrick, for example, the Earth, no planet orbits, no moon orbits. Orbits do not occur in circles. For example, Copernicus thought they did. Before Copernicus, they thought Earth was in the center of the solar system and everything went around the Earth. He said, no, Earth goes around the sun, moon goes around the Earth, but he had circular orbits. Johannes Kepler got to studying the data and he realized orbits are not circular. They are elliptical. Now, an ellipse is like an elongated circle, and the thing that's being orbited is at one of the two foci. You have a focus here and a focus here inside the orbit. And when the moon orbits the Earth, for example, the Earth is at one of the two foci. So that means that there are some times when the moon is closer to the Earth, sometimes when the moon is further away from the Earth. Same with the sun. The Earth sometimes reaches proximity to the sun. Right now, we reach our greatest proximity to the sun in early January, believe it or not. Early January. And that's winter in the Northern Hemisphere. You might think, well, if we're closer to the sun in early January, why is that winter? Well, that's winter because in early January, even though the Earth is closer to the sun than at other times, the Northern Hemisphere is tilted away from the sun. The Earth is tilted on its axis 23.5 degrees. a few thousand years ago, 20,000 years ago, let's say, the Earth's closest proximity to the sun was not in January. It was not at that time of year. It's called the precession of the equinoxes, where the time of year in which the Earth is at, it's called, perihelion. Perihelion is the time we're closest to the sun. It's the first week in January. Aphelion is when we're furthest away. Now, because the northern hemisphere has most of the land, we've got most of the land. The southern hemisphere is mostly ocean. That has an enormous impact on the amount of radiation from the sun that is captured on the surface of planet Earth, and therefore changes the time of year in which the Earth is at perihelion, has an influence on climate. Also, the tilt of Earth's axis at 23.5 degrees, it's not constant. There are times when it's over 24 degrees. It's a greater tilt. As you probably would imagine, the greater the tilt, the more severe the seasons. If we weren't tilted at all, if we were just perpendicular, the pole was perpendicular to the orbit, we really wouldn't have seasons at all. The reason we have seasons is because of the tilt, but the tilt doesn't stay the same.
I see.
The eccentricity, the amount of elliptical, doesn't change. The perihelion date does not change, changes, is not constant, and the tilt. And when those things come together in a certain way, it means a lot more radiation is captured by planet Earth. And that's what's going on now. And that's why we're so warm. But 35,000 years ago, we had a greater tilt, we had a different perihelion date, and we had a different amount of eccentricity to the orbit. And that's what causes these changes. Milankovitch cycles. And I encourage everyone to Google Milankovitch. He was the Serbian astronomer that figured all this out. And that's what causes these ice ages. Now, as you know, Patrick, what we're doing, we're starting out on the very long term. We did 600 million years last time. Now we're down to 800,000. We know that continental drift caused the changes over tens of millions of years. We know that over hundreds of thousands of years, it's the Earth's orbital changes. That is the changes in Earth's orbit. The previous ones I showed you on hundreds of millions of years were caused by continental drift. So there are different things that determine Earth's temperature at different time scales, is what I wanted to get at. I wanted to go through that, and I also wanted to point out the context, which is the magnitude of these. You can see at the Ice Age, when most of northern Ohio was under ice sheets, it was only 9 degrees Fahrenheit cooler. That 5 degrees Celsius, -5, 20-some thousand years ago, that's not, you multiply that by 9/5 to go from Celsius to Fahrenheit. And of course, the fives cancel, you get 9 degrees. It was 9 degrees cooler. Then that's the difference between northern Ohio, Pennsylvania, Minnesota, all these being under permanent ice for thousands of years, and the kind of Earth we have now, only 9 degrees. I wanted to do that because what I wanted to say was, when people talk about a 2 or 3 degrees fluctuation, some folks say, well, that's nothing. It fluctuates 30 degrees between yesterday and today, but the whole planet doesn't. The whole planet doesn't. When I talk about a 2 to 3 degrees change in global average temperature, that's a completely different phenomenon than a 2 or 3 degree change at one location. Okay, so that's something that it's kind of hard for people to get into their minds. You know, you say, well, who cares if the Earth warms up 8 or 9 degrees. Well, if the Earth warms up 8 or 9 degrees, we're into catastrophe. Even though it may be 30 degrees warmer in your hometown now than it was a few days ago.
Well, that makes a lot of sense.
Thanks for the question about the sun and the Earth's orbit. Just to remember that Earth's orbit does go through changes. And a lot of those changes are caused, that gets into astronomy, which is fun. The position of Jupiter relative to the Earth, it's so massive. Its position tends to tug on the Earth and influences Earth's orbit. It's part of Milankovitch forcing. There are a lot of factors that influence what the Earth is doing in its orbit around the sun, but it does change over the period of about 100,000 year cycles. And you can see that's why we had a warm period 100,000 years ago, like the one we're in now. You go back 200,000, you see a peak there, 300,000, 400,000. Those are 100,000 year cycles called Milankovitch cycles. And yes, this is another thing I wanted. Somebody called me up when they saw my first show last week and said, I got a book from the 1970s and 80s that said the coming ice age. And now you're talking about warming. And I told them, yes, Earth is programmed. You can look at this graph and see that Earth is programmed to go into an ice age because that's the way Milankovitch cycles work. If you kind of analyze it, it looks like maybe sometime over the next 10,000 years, we could very well plunge back into another ice age. But that's not something that's going to happen in the next 50 to 100 years. That's something that we're programmed to do. But because the Earth's orbit is continuing to go through Milankovitch cycles, that hasn't stopped. But what we're going to get up to now are other changes, like you mentioned, solar activity. And then ultimately, we're going to talk about human activity and how that's affected. So we're on this knife's edge. You know, we're in Icehouse Earth. The array of the continents is not going to change. We're going to have a cold Arctic Ocean. We're going to have a cold Antarctica that will give us a lot of cold air coming. We're between ice ages and a mild interglacial that is due to end very soon as in the next 10,000 years on the big scale. And the downward temperature trend already began. This is the temperatures that we've seen since the end of the last ice age. Again, way out to the right is 0 years ago. Way out to the left, we're talking 18,000 years ago. So the warming began around 25,000 years ago, and it went over about 7,000 years. It warmed up about a degree Celsius over 7,000 years. Now, to put that in context, that's about 1.8 degrees Fahrenheit. Well, we've warmed 1.8 degrees Fahrenheit now since the Civil War, 150 some years. And it took from 25,000 years ago to about 18,000 years ago to warm just 1 degree Celsius. And if you look, you can see there were some upheavals about 14,000 to 12,000 years ago that almost caused us to go back into another ice age. If you see that big drop, that's an anomaly that was probably caused by disturbances in ocean circulation due to melting glaciers that changed the salinity of the surface of oceans and cooled the oceans dramatically. But the Milankovitch forcing ultimately won out 5,000 or 6,000 years ago. We got to the Holocene maximum. That's when we invented agriculture and writing. Since that time, we've had some warming, the Roman era warming, the medieval warm period, and the Little Ice Age. And we've come to where we are now. These are actual studies that each color is a different study. Each color is a different study that has tried to replicate temperatures over the last 2,000 years. So now on the right, we've got the year 2000. And way out on the left, we have the year at the beginning of the Common Era, AD, if you want to call it that. And each color shows reconstruction of global temperatures. So basically, I want to end this one today on, if you look at what the difference between human-induced warming looks like and natural warming, look at the black line out to the right. The black line out to the right is what's happened since the Industrial Revolution. If you look at all the other lines, you can see there's warming and cooling. Yeah, it's natural. But look at the black line. That's the actual climate temperature data since the time of the Civil War. And look at 2016. Okay, look where we are compared to where we've been. If I had a graph, Patrick, that could show you the difference between human-induced warming by putting CO2 into the atmosphere, enhancing the greenhouse effect, and those natural warmings that we've been talking about. And again, most of those up and down, you can see they're in a very small, they're only like 2/10, 3/10, 4/10 of a degree Celsius, because we're talking about a shorter period of time. It's not common for Earth to change 8 or 9 degrees Celsius in a few hundred years or even 1,000 years, as we saw before. Those changes of those magnitudes take a lot longer. But I want to leave you today with the warming out on the right. You don't need to be an expert in trend analysis to realize that looks different. The black line looks different. And the 2016 number, that whole trend looks different than previous. And that's the difference on a signature between human-induced warming caused by CO2 and warming caused by nature. You see the medieval warm period and the little ice age?
Yes.
During the little ice age, around 1600, Galileo and those guys started studying the sun. And they started counting sunspots. You mentioned a while ago, what role does the sun play? The overall view is that that little ice age was caused by a reduction in solar output. It's called the Maunder minimum, Maunder, the Maunder minimum. In other words, the amount of sunspot activity around the year 1000 in the medieval warm period, the amount of solar output activity was greater then, and it started to decline around the 12th, 13th, 14th, 15th centuries. It's believed that the little ice age, which caused the River Thames in London to freeze, rivers in the United States froze every winter, the Ohio River, when the early explorers came here, and even in George Washington's time, he wrote about rivers freezing, and the Delaware River, which he crossed in the Revolutionary War and the Battle of Trenton. All those were caused by a low temperature that we call the Little Ice Age, which was driven partly by ocean currents, but also partly by solar inactivity called the Maunder minimum. The solar output started to pick up, a little bit after that. But what's happened in the past 40 years in our lifetime, okay, as we get up to look now, solar activity has actually been going down since the 1970s and 80s. It's in a cycle. The sun's in a little bit. The sun's more active now than it was in 1600, as you can see on the graph. Part of that's the sun, okay, that did that ended the medieval warm period. But in our lifetimes, Patrick, solar activity has been going slightly down, not dramatically, but it's been slightly going down. I'm much more sensitive to heat now than when I was a kid. When I was a kid, I loved the summer and getting out in the heat. I can't do that anymore, but it's not because of a more powerful solar output. Solar output, the past, and we're not up to that yet. We're still doing some of these earlier time frames. Next episode, as you can see, we're getting closer. We started out 600 million years ago in episode 1. We're getting a lot closer, and you can see we've even got 2016 on here. And next episode, I'm going to bring you up. We're going to talk about 19th, 20th, and 21st century temperatures specifically. And I'm going to give you some of the reasons, in addition to human activity, that have influenced global average temperatures.
Hey, I'm really looking forward to it. Hey, we're talking with Dr. Thomas Blaine. Dr. Thomas Blaine is an associate professor with the Ohio State University, and he is phenomenal in helping us to understand global warming and climate change. We hope to see you at the next episode. I'm Patrick Dangle. Thank you for watching.